Following one of your classmates' requests, this is a brief video to review power series. You might notice that it has been done with a different technique than usual videos. This is to ensure that I can publish them faster, and I hope it's still going to have a good quality and you can be able to follow it. So let's talk about power series. Let's start with the idea of why we want to talk about it. We're thinking about the idea that if we have a function around a point that we know, so around x0, we are assuming now that, for example, x0 is a real value. If we have a function and it has enough derivatives, we can write the Taylor series of this function. So we know that f at x can be written as a f at x0 plus f prime at x0 times x minus x0 plus other terms. If this function is analytic, it means that the Taylor series converges to the function in a neighborhood of x0. Why is this useful? Because then we can talk about, we can approximate f, at least locally, by a power series of f. So we go from asking what is f of x to asking what are the coefficients in front of x minus x0 to the power k. So we have changed the setup from having no idea of how f looks to, if we know ak, that is the coefficients of our infinite series, we actually know f in the neighborhood of x0. We don't really know how big this neighborhood is, but it's a good starting point when we're talking about ODEs, because in ODEs we know the existence of the solution locally, and then we can kind of stretch it step by step. And this is what we can do in special cases. In general cases, we can just assume that the solution has a power series format and try to find the coefficients of this power series. So when we're talking about power series in ODE setting, what we have is an ODE of the form, we're looking for y as a function of x. In the cases we usually consider, y is a function of real values, so x is real, and it returns a real value. That makes it easier when we're talking about derivatives and so on. And we expect to have a special point x0, and around that special point we're assuming that y can be written as a power series. So y as a power of x, as a function of x, can be written as an infinite sum from k going from 0 to infinity of a k x minus x0 to the power k. And now we have shifted our problem from knowing y to knowing this infinitely many coefficients a, k. And we want this to satisfy a given ODE. Something that would look like a function of x times y second plus another function of x times y prime plus another function of x times y equal potentially another function of x again. Each one of these f1, f2, f3, and f4 can be written as a power series. So we change this problem that is a linear ODE, potentially with f1, f2, f3, and f4 being nonlinear. So it's a linear ODE with non-constant coefficients. And we change that to a problem in which we want to find the coefficients of the power series of y. So we change this into writing f1 as a power series. So there would be a sum from k equal to 0 to infinity of some coefficients multiplied by x minus x0 to the power k. I'm going to call it, so we are using a for y, so this is going to be b, k, x minus x0 at the power k, and y second is itself a power series. So at the moment I'm just going to write it as the second derivative with respect to x of the power series of y. So sum for k equal to 0 to infinity ak x minus x0 at power k. And then for every single of the other terms, we also want to write it in the same format. So we'll have a similar term for f2 of x, a similar term for y prime, and so forth. In the very general setting, this is really complicated to solve because now we have the product of two infinitely long power series. If f1 is particularly nasty, it might have infinitely many elements. Luckily, we usually concentrate ourselves on finitely many power series. But in order to work with this, we need more information about how to handle power series. So one of the first things we want is how the products work, because now we have the product of f3 multiplied by y, and if f3 is a power series and y is a power series, we need to know how their product works. So our first statement will be if we have a power series ak x minus x0 to the power k and a power series bk x minus x0 at the power k, what is their product? Well, it turns out that, luckily for us, the product of two power series is still a power series. So we're going to write it as ck x minus x0 at the power k. But what is ck? Well, ck is not very easy. It is a sum for, we're going to change coefficient for n going from 0 to k itself. And what we want is that the product of the element, the index a times the index b would give us the k. So we're summing element by element as we do for normal polynomial products. Just in generality, it brings us to have n equal to 0, sum from n going from equal to 0 to k of a and b k minus n. So you start with a0 and bk, and then you go a1, b, k minus 1, and then all of them, until you get to the other opposite, a to the k, b to the 0. So we know how to do products. Then we have to know how to sum things together. And the important element when you're summing things together so we're summing I'm forgetting a power here. We're summing two power series. What we need, the very important element that we need, is that their powers are the same in both cases. If the boundaries are not the same, then we have to adjust it. So if, for example, this was for k going from 1 to infinity, then we have to adjust it in the sense that we have to introduce either we split it with k going from 1 to infinity for the first series as well, or we have to add the 0th term to the b series. But in general, what we really need for things to work is the powers to be the same. So once we have reorganized our series such that x minus x0 at the power k appears in both series, and k can change name, but the important thing is that it's the same as the iteration element that you're considering, then if you have this, then the sum of these two things is the sum from k equals 0 to infinity of ak plus bk x minus x0 at the power k. So if we're able to rewrite our problem as a sum of power series with the same powers in the series, then we're able to sum it correctly. And the last element that we really need is what is a solution. And this goes with the statement that if you have a power series sum for k going from 0 to infinity of ak times x minus x0 to the power k. And if you have this equal to another power series, then it has to hold that ak is equal to the two coefficients of the two different power series are the same for every single k from 0 to infinity. There is a special case to that statement. The special case is when you have a zero power series. So you have ak x minus x0 to the power k equal to 0. Well, if that is the equality you have for the power series, then you need ak equal to 0 for all k. So our job is taking the general ODE that we have, assume y can be written as a power series, multiply all the things together, create new power series in a form that we can sum together, and set them equal to 0. Then we know that the coefficient of the new power series that we have constructed has to be 0 all the time. So let's try to look at how that works. So let's say that we have y second plus xy prime equal to 0. The first step is the assumption that we take an x0, whatever we want. Usually we take x0 equal to 0 because that makes our job a bit easier. So I'm going to take x0 equal to 0, and I'm going to assume that yx can be written as a sum of a and x minus x0, so x minus 0, we can just write x, at the power n. If this is the case, then we can write y prime and y second. The derivative with respect to x of a power series is the power series of the derivatives. So this can be written in a lot of different ways. And when we're going to be working on the power series, we'll have to find different ways of writing the same power series such that the next steps can work. But this, between other ways, can be written as n from 1 to infinity, a n times n x to the n minus 1. So I have taken the derivative of every single term of the power series. And the second derivative can be written as n equals to 2 to infinity of a n n n minus 2 x to the power n minus 2. So now that we have this, we can plug it in the example that we have. And we have that we have the sum from n equals 2 to infinity of a n n n minus 2 x at the n minus 2. So now we have the second derivative of y. There is no coefficient in front, so we don't have to add any other power series. And then we go to the second term, and x is its own power series. It just has one term. So we're just going to write it as x times y prime, that is sum for n equals to 1 to infinity of a n n x n minus 1 equal to 0. Sorry for mumbling all together. I'm going to move it here. And now the goal is finding a way to summing these two power series. So we want this coefficient and this coefficient to end up being the same. And we have to remember that there is an x in front. So the first thing is we're going to get rid of the x in front of the second power series. So we have sum for n equals to 2 to infinity of a n n n minus 2 x n minus 2 plus sum for n equal to 1 to infinity a n n x to the n equal to 0. So this second power series is quite nice because we have the power of xn being the same thing as the thing we're summing. So we're good in that aspect, it looks pretty good. What we don't like is the first power series because this is an n minus 2, while the second power series is an n. So we have to equalize them in some ways. So what we want is changing the first power series in such a way that we can have x to the power n. And that is... Oh, I copied wrong. I did quite some things wrong. This is a -1, not a -2. -1, -1, -1. So if we're looking at the first power series, what we notice is that if we shift for n going from 0 to infinity, the first term would have n multiplied by something. So n equal to 0, so we don't have anything. And the second term would have n minus 1 multiplied by anything. So if n is equal to 1, that would be 0 multiplied by something. So the first two terms would be 0. That doesn't solve the fact that we start with here n at the -2. But maybe that helps. Let's start by rewriting the first term as sum from k going from 0 to infinity of a k times k minus 1 x to the power k minus 2 plus the second power series we might want to start at n equal to 0. So we have the same starting point for both power series, and we can just change it because of the first element of our power series, that is n equal to 0, we have n multiplied by something, and if n is 0, then the whole term is equal to 0. So this we can go from n equals 0 to infinity, a n x to the n equal to 0. So let's try to work out of the first term in such a way that we change our power to be not k minus 2, but k. How can we do that? We add a new we add a new index. We go from n equals to, well, we want to go for k minus 2. Actually, maybe going to k equal to 0 is not a great idea. We want to add, so we want to m to be equal k minus 2. So if we start at 0, we have m starting at -2. That is not nice. Instead, we're going to start at 0 because the first two terms are 0 anyway. So here we have a k, but we have the equality m equals k minus 2. So here is m plus 2, k becomes m plus 2, k minus 1 becomes m plus 1, x at the k minus 2 becomes x at the n, plus sum from n equal to 0 to infinity, a n x n equal to 0. And now we have two things that we want. We have the power being the same. I mean, one is an m, the other is an n, but we can change the name given to the indices without problem, so they are the same thing. And our power series start at the same point. So that's two positive things that we can have, and now it's very easy to sum them up. So we can write sum for k equal to 0 to infinity of the sum of the two coefficients, and then we have x to the k equal to 0. So we have a k plus 2, k plus 2, k plus 1 for the first term, plus ak times k for the second term. And now that we have an infinite power series being equal to 0, it means that every single coefficient of our power series is equal to 0. So we have that a k plus 2 times k plus 2 times k plus 1 plus ak times k is equal to 0 for k going from 0 to infinity. This is a recurrent relation. Most of the times, this is as far as we can go. The recurrent relation might be pretty complicated. We keep it like this. If we had something that is a power series itself on the right-hand side, k equal to 0 to infinity of ck x to the k, then we would need this on the right would be our non-homogeneous term. so we're changing the problem to add a non-homogeneous term, then our recurrent relation would actually be that the two coefficients of the left-hand side and of the right-hand side need to be equal. So handling non-homogeneous terms with power series is actually quite easy.